So with all of this, let's quickly look at what the AXI DMA controller itself looks like, right? Again, as I said, we are not really going to go look into too much detail on code. I will be showing a couple of snippets of code, but primarily sort of looking at it from the point of view of what are the registers and what we need to do. So the DMA controller has, as we saw, MM to S, from memory to AXI stream, which is basically the peripheral, and S to MM, which is, we assume that the peripheral is sending data into an via an AXI stream to memory, right? And we basically have several registers that are set up per channel, and the interesting thing is this controller, one block, can basically handle multiple different channels of communication at the same time. So even though it is a single bus master, it could potentially be handling many different data transfers all at the same time. And this is an interesting design choice. It basically says, look, anyway we know that memory transfers are expensive, why not let a whole bunch of them get queued up, right, sit over there, and then the CPU goes away and does its own thing, and as and when each one gets completed, the CPU can be alerted through IRQ, and maybe the DMA just switches over to the next channel and continues, right? Or if you have different channels where the data is coming in at different rates, or one of them has back pressure due to something not being ready, I switch over to another channel and continue, right? All of those are possible now, at least. So there is, as usual for all the devices that we have seen so far, there are typically control and status registers, right, which are very common. It's a common design pattern which is used, right, for pretty much any kind of peripheral that needs to interface with a memory mapped system. Apart from that, the main things that we really need are the addresses, source and destination physical addresses, and the length of the transfer, usually in bytes, right. Now just to sort of recap, right, I have been talking about AXI stream so far. It is possible to have DMA transfers without AXI stream, right. What we can do is what's a so-called direct memory mapped DMA, right, where we are essentially doing a large memory to memory copy, right. So I have an array sitting somewhere in memory, I want to copy it into another chunk of memory. Now by itself probably not very common, in the sense that it's unlikely that I would just be copying data from one set of memory addresses to another, although it does happen. There can be many scenarios. There, especially when it comes to peripherals, this actually becomes somewhat common. One example would be that you are sort of trying to build up an entire video frame in some memory buffer by performing some computations and maybe graphics rendering and so on, and finally you want to copy that into your video engine, right. So that's a prime example of a memory to memory copy, but you could also have things where you just have even something like an editor or a spreadsheet where I need to sort of make copies of large chunks of data, right. All of that can be handled very efficiently by DMA. So you could either have direct memory to memory, or if the peripheral itself has been memory mapped, you could do a DMA which basically says take a chunk of data and do a bulk copy into the memory mapped buffer that corresponds to the peripheral. Now an important thing to understand over here is this word burst, right. The AXI Lite protocol that we talked about earlier, it allows us to do this memory mapped buffer window for, let's say, even the FIR filter, that was data in and data out, which looked like memory mapped windows. The problem is, because they follow AXI Lite, it means that I need to give an address, I need to give the data, I need to wait for a response, and then I need to move to the next data. The full AXI protocol, on the other hand, not AXI Lite, the full AXI protocol supports something called burst mode, which allows me to basically say, okay, I want to transfer 16 words starting at this address, and then the bus by itself will take care of incrementing the addresses and moving forward to the next location, so that I can just basically do a bulk transfer very quickly from one chunk of data to another chunk of data, right. So very similar to what we think of in terms of the stream, right. Essentially we would be generating multiple addresses consecutively. The DMA engine takes care of just generating addresses one after the other, right. So the read address, write address, all of those are taken care of properly. So we can actually do this business of transferring chunks of data in bursts, provided we have the full AXI protocol support. AXI Lite by itself cannot do it. If we do use this burst mode, then it is possible to have more or less similar performance to what happens in the case of streams. Okay. Now, the advantage of this is, especially if you are doing block copies, it can use bus bursts very efficiently, right? One problem is, as I had noted earlier, this whole idea of frame handling using the T-last signal is something that comes naturally with the DMA, right? But over here we don't, or rather the stream protocol. Here that's not part of the protocol by itself. Or rather we can just basically do exactly, we copy exactly the, whether this is a pro or a con is depending on the kind of application. You might decide that you don't want to sort of wait for a separate T-last signal and process it, you just exactly transfer the amount of data that you have. The problem is, whenever you have either variable rate producers or even continuous pipelines like an A to D converter, I don't really have a sequence of addresses to read from. It's always coming from the same memory location, right? So a stream is a more natural fit for that, right? Which means also that the peripheral itself must expose a burst capable window. An A to D converter probably exposes a single register and says, okay, read from this, every time you read you will get the next sample, right? Whereas if I want it to be the burst mode transfer, I actually need, let's say, at least 16 addresses and say, okay, if I read from these in burst mode, I will get successive samples. So of course these are implementation issues. At the end of the day, if you go deeper and look inside the IP, you will probably find that both get handled in a very similar way. It changes the way that you think about the implementation, that's all. In general, streaming accelerators are probably a fairly common thing to think about now, right? The filter, FFT, most neural networks fall in this kind of category, right? But if you do have sort of block operations where I just want to transfer a chunk of data, then bursts may make more sense than the stream, right? I actually want to copy data from one chunk of memory locations to another chunk, right? So in general, both are available and how you use them is up to you. So a quick recap of a quick look at what the typical DMA register map for the the DMA IP used by Xilinx looks like, right? Now, as you might imagine, there are like very few registers mentioned over here. The actual full data sheet contains even more than this. But the interesting thing is that there are a few that are really important registers. There is the control and status register for MM2S, right? It, for example, allows you to actually make the DMA, set it up, right, move it into running mode, enable IRQs. The status register tells you whether the system is idle and also whether IRQ has been activated and so on. And then you have two registers which basically say what is the source address. Remember, this is an MM2S, right? So I need to read from a source and send the data out to a stream. I do not need a destination, right? So the MM2S source address and the length, and the DMA is usually set up such that as soon as you write into this length register, it starts transferring. Again, design choice, right? Not necessary that this is the way to do it, but it's actually a nice simple way of doing it, right? You know that I have got this AXI handshake which tells me something got written into the length register, and when that happens, I trigger the actual transfer. Same way, S2MM, I have control and status. I have a destination address now because I am reading from the stream and putting it into memory. And when I write into the length register, it reads that many words, puts them into memory and stops. Okay. So just to sort of put this in the context of our FIR filter, this is typically how you would implement something of this sort. You would go and write the RTL for your filter in such a way that it receives input on AXI stream and gives output on AXI stream. No more addresses, no more AXI Lite or AXI bus associated with the FIR filter. It has a very clean data in, data out kind of interface, right? And is purely data driven, right? And then the actual input basically goes in through MM2S, through the AXI stream, processed by the filter, goes out into another AXI stream to DMA, which converts it back into memory map and puts it into the actual memory of the system, right? So the FIR is now simplified. It doesn't have data in, data out registers, it doesn't have a control, it doesn't have anything else. As and when it receives valid data over here, it performs, this is the next sample that came in, it performs all its shift, add, etc., and gives back an output over here. So it's completely data driven. Right? Now in order to use something like this, we would need to go through some standard code in the kernel, one of which would be that you need to actually allocate appropriate buffers, for example the input buffer and the output buffer, right. And what happens over here is this FIR input buff and FIR output buff are set up in your driver probe, right, when you are actually initializing the driver. Now these are actual pointers, right, and they refer to buffers, which means that I need to be able to take data. Maybe I am reading it from, I have an echo 1000, 2000 greater than something. So there has to be maybe a parse function which is going to read out the data, or I might have something else which basically tells the driver, right. Maybe I do a copy, a file copy, right, which basically says, okay, now read from this file and just dump the data into this location, right. Either way, the input buffer, in other words, is a virtual address, it is a pointer, it is a virtual address inside the driver, right, which is used by the rest of the Linux function calls. This input DMA on the other hand is a physical address, right. So what the DMA allocate coherent ensures is that it gives you a pointer but also tells the kernel to treat whatever pointer is over here as something that should not be cached, right. In other words, whenever I am trying to read data over here, I should be directly going to the physical address location and either doing a read or write as required. Okay. Same with the output buffer, right. Now obviously when we allocate coherent, we also need to free coherent at the end of the day, typically when we are unloading the driver. Now how do we go about starting a DMA transfer? Well, we need something to indicate the length of transfer, right, and then we want to transfer data into the FIR filter, right. So what we do is we basically say, okay, write L. Why is this write L? Because it's actually still just a control register setting. So this write L is used over here because I am trying to write into this memory location or this address to set the mm2s SA register of my DMA module, right. So I have the DMA base address, I go to the address of the source, the location of the source address register and put the physical address of my input DMA over there. It has to be the physical address, not the virtual address. Then I write the number of bytes to be transferred, and remember how we set things up. The DMA module is written in such a way that the moment I write into this register, this transfer actually starts. Okay. Now how does DMA work? I don't need to wait over here, it's going to write and it's going to move on. Okay. So I immediately after that also set up a S2MM transfer where I say, okay, now that this is done, let me also go set up the reading back the data, right, which means basically give the output DMA address to the MM to DA or S2MM destination address, right, and tell that the DMA module how many data it expects to come back from there. Okay, once again that's a write L, and I have just configured the DMA, I move on. After doing all of this, I set a flag saying that the FIR is currently processing, right, and somewhere above all this, in fact usually in the driver probe itself, I would normally have already set up the IRQ enable and so on, which basically tells the system enable all the IRQs, set things up such that as and when these things get completed, they will interrupt the processor. Okay, which means that as and when the DMA is completed, I need an IRQ handler, right, which will get called. I'll have to register it properly in my driver code and so on. What it will do is it will basically check the status, and if the IRQ was that the S2MM has completed, right, or rather if it is that the S2MM has completed, it will proceed over here. If not, it will just return none, right. Assuming that this IRQ has actually, it was the correct IRQ, you first clear it, you set the processing to false, and then you wake up interruptible on anybody who was waiting on this. In other words, you probably had a wait queue somewhere that was waiting on this. Why are we doing this? Remember that an IRQ handler cannot by itself do anything complicated. So I cannot be having something which sets up another DMA or does something else inside the handler. All that it does is it pretty much releases this FIR processing, says okay, it's false, which means that I can probably, at any other part of my driver, if I need to check and maybe initiate a new transfer, I can do that, right? And also I have woken up things that were interruptible or were waiting on this particular IRQ. So if, let's say, I wanted to transfer my next chunk of data, that would have been sleeping on this particular wait queue and would be woken up and told, okay, now you can send some more data into the FIR filter. Okay. So this combination essentially allows us to handle transferring chunks of data into the filter, getting them processed, and then finally having the CPU get alerted once it's completed. Now what this also means is that we can also have our typical sysfs interface, where I would typically do something like parsing the values that I am writing into the FIR input buffer, which is where the DMA reads from. And I could, for example, have a blocking data show function, which would wait for the FIR wait process or FIR wait queue, right, and then copy from here whatever has been written in by the DMA, copy from the FIR output buffer and maybe display it or do anything else with the data. Okay. The important thing is I do not have to do readL or writeL. I do not actually sort of do any of those steps inside these functions, because the actual movement of data has been handled already by the DMA.